In this presentation, we will explore the concepts of spatial and contrast resolution as they relate to digital radiography. Under older paradigms, spatial and contrast resolution might also be known as detail and visibility of detail, respectively. Before we start, there are a few rules to consider. They're not hard to remember and make abundant sense. Larger objects are easier to visualize and accurately represent in digital radiographs. This is true of objects regardless of their relative density to their surroundings or composition. Also, larger objects are comprised of more pixels, and this increases the likelihood the computer will emphasize them in post-processing. The obverse of large is small, and smaller objects are more difficult to see. We are fortunate in radiography that we will not be looking for very small objects often, less than a millimeter in size. The more the density of an object differs from adjacent or underlying structures, the easier it is to record or visualize. An object can be darker or lighter than its surroundings. The importance is the amount of difference. Again, the obverse of high contrast is true. The reason we don't see blood vessels on standard radiographs is that they have density similar to the surrounding tissues and are not visible without enhancement or contrast media. First, let's take a look at issues of spatial resolution, or as it was previously known, detail. Larger objects are easier to see, but also easier for the computer to render. All graphical objects on a radiograph are made of small square dots called pixels. The larger an object is, the more pixels participate in its rendering. Curves will appear smoother and the object will be rendered more accurately. Finally, larger objects are just easier to see. Note the object on the right of the screen. The larger one looks like a circle with a notch removed from its left side. The smaller object is the same shape, just reduced in size. Can you see the notch? I assure you it's there. If I magnify the smaller object, you'll see the notch become visible. Notice that the smaller object is not rendered accurately when magnified. It appears blocky and blurry. In computer graphics terms, this blocky appearance is called aliasing. This is because the image is made of many fewer pixels than the larger version and cannot be accurately displayed without pixels becoming visible when it is magnified. Relative position of objects plays a major role in spatial resolution. Not only object to image distance, but also the relative position of one object to another. Remember, in radiography, we are projecting a three-dimensional object onto a two-dimensional surface. This means that images of overlaying or underlying structures will be superimposed on the object of interest. In radiography, this problem is often overcome by providing oblique views or angling the tube. The circle on the left is a composite of 4 ovals. The reason they appear as a circle is that they share similar density and are superimposed. I'll color each oval to highlight its shape and orientation, and then separate each so that you can easily confirm their true shapes. Finally, the bottom oval is 2 ovals superimposed. I will separate them to highlight their true appearance. It's too bad we can't do this on a real radiograph. In radiology, we measure resolution in units of line pairs per millimeter. For more information regarding resolution measurement, refer to my Foundations of Detail video. For an object or line to be reliably recorded and not ignored by the computer, it needs to span a minimum of 2 pixels. The grid above represents 4 pixels from an imaginary imaging device. In this example, half the radiation reaching the pixel must be stopped before the computer will register the image of the object. To keep things simple, objects in this example are penetrated by about 25% of the radiation. This first dot is a pixel in size and spans the 4 pixels. Less than 1/4 of each pixel is masked by the object. Below is a representation of what the computer records. The dot is completely ignored as background noise. It covers less than 50% of the pixel and 25% of the radiation penetrates the object. If it were a linear object, 1 pixel in width, it would also be ignored because it would cover 50% of the pixel with 25% of the radiation penetrating the object. This dot represents the only situation where a 1 pixel dot gets recorded. In this example, the dot aligns exactly with the pixel. If the 1 pixel line were to align exactly with the pixel, it might also be recorded. The chances of this happening are rather low. Chances are better the line would span 2 pixels and be ignored. In this scenario, the dot is recorded because it aligns exactly with the pixel below. If the dot were aligned, the line would also be recorded. What is the likelihood of this alignment happening? Not likely. This oval spans 1 pixel wide and 2 pixels high. What is the likelihood it will be recorded? The likelihood it will be recorded is very high because it spans 2 pixels and is sure to cover one of the 2 and more likely be recorded. If the object were a 2 pixel line, coverage of 1 or 2 adjacent pixels is a certainty. This circle represents 4 pixels in diameter, 2 pixels up and 2 pixels across. It is recorded because all 4 of the pixels are masked. If it were off-center, 2 of the 4 pixels would certainly be recorded. If this were a 2 pixel line, it would most certainly be recorded, but not as thick as the actual object. In conventional radiography, objects 1 or 2 pixels in size are generally of no consequence. One example where small calcifications are important is in mammography. So the more pixels an object spans, the more definite it will appear in the radiologist's workstation. Increasing the number of pixels covered can be accomplished by making the pixels smaller. Here is a listing of common resolutions of a number of CR and DR imaging systems. Note that the highest resolution is the AGFA DR mammography plate at 6.5 line pairs per millimeter. This is a little above what the unaided eye can see without magnification. The lowest is the Konica Aero DR plate at 2.5 line pairs per millimeter. Objects may be recorded by computerized radiology systems, but not displayed in a manner that is visible to the observer. At times, manipulation of window level or window width will bring them out, but this is not always the case. It is the responsibility of the radiographer to maximize the contrast resolution of all images. Noise has a large negative effect on contrast resolution, and noise is something the radiographer can reduce with proper technical practices. The largest source of noise on radiographs is fog. Fog production is most effectively controlled by collimation. Collimation must be used on every radiograph we produce. Next on the list is grids, but the use of grids is not beneficial for every view. Anatomy under 10 to 15 centimeters does not benefit enough from adding an exam. Also, grids increase patient dose by 2 to 4 times. Finally, filters have a nominal effect on fog production, and most radiographers don't have access to machine filtration as it is set by the manufacturer. The conversion of radiation into a digital signal requires several electrical transformations. Along the way, noise or random signals can obscure the image. Computer algorithms are implemented that allow the computer to ignore signals thought to be noise. Increasing the ISO rating, effectively speeding up or increasing the sensitivity of the imaging plate, will increase noise. Much like taking a photograph in a low light situation where the image becomes mottled or grainy. MAS is a calculation of how many X-ray photons are used to produce a given image. Doubling the MAS doubles the radiation dose used to produce an image. Digital radiographs are often display a grainy appearance called quantum model, which is a form of digital noise. The way a radiographer can help the computer separate the image from noise is to increase the number of X-ray photons hitting the detector. Simply put, increase the MAS, but increasing the MAS to a point. That point is where the image displays an LGM, REX, S number, or DI number within the manufacturer's recommended range. Producing an out-of-range image either displays excessive quantum model or subjects your patient to excessive radiation dose. Here is a moderately collimated PA chest with a high signal to noise ratio. I've just now added 20% random noise to overlay the image. Notice the changes to the image are subtle. There is noticeable contrast loss. While lung markings are visible, they are not as prominent. When we again double the noise, there is a marked loss of contrast. It is very evident that lung markings are being obscured by the noise. Finally, here is an extreme amount of noise applied to the image. Notice how lung markings and even some of the ribs are not visible as on the initial image. Now let's do a noise comparison using a less complex object, large dots. In this example, the dots are about 1.5 inches on my monitor. Their actual size will change with the size of the monitor that you are using. Some of my observations may also vary with your monitor size and quality. Presently, there are 6 rows of dots. Each dot is 2 times darker than the one to its immediate left. I've just overlaid rows 2 through 4 with random noise. Note how the dots in column 1, 2, and 3 have disappeared in the 80% row, as have the dots 1 and 2 in the 40% row. While all the dots are visible in the 20% row, the darkest dot appears lighter. This dot is not lighter, but has lost contrast with its surroundings. Loss of contrast is the loss of visibility of the dark or high contrast densities. This matrix is exactly the same as the previous except for one important difference. The dots are about 10 times smaller. Pay attention to the first column of dots. They are barely visible without any fog added to the image. On the large dot slide, they were visible. Now smaller, their visibility has changed. When various levels of visual noise are added, different levels of visibility are evident. For the 20% row, the first two columns are obscured. The 40% row has lost the first three columns, and the 80% row has only the dot in the last column still visible. Here is a size and contrast matrix. As we move through the 6 columns from right to left, each dot is 2 times darker, and as we move down vertically through the 7 rows, each dot is 30% smaller. According to what we have seen, the large dot in the upper right corner will be most visible, and the dot in the lower left corner will be most difficult to see. Here is the matrix without any noise. With the noise added, the bottom 3 dots in the first column are not visible. Also, the bottom 2 dots in the next column are obscured. Now let's observe the matrix again with a 40% noise overlay. Again, here is the matrix without any noise. With the 40% overlay added, the first column, except for the largest dot, is gone. The second column, except for the top 2 dots, are gone. Again, supporting the contention that size matters when considering visibility of detail. Let's take one last look at the resolution matrix using the 80% noise overlay. Finally, here is the matrix without any noise. In the extreme condition, the first 3 columns are gone. In columns 4 and 5, the bottom dots are obscured. As we saw in the Fundamentals of Detail video, object image distance, source to image distance, and focal spot size affect detail. But also an object size relative to the pixels recording it also makes a difference in its visibility. An object's actual size governs the number of pixels that represent it in the final image. The more pixels that make up an image, the more likely and more accurately it will be recorded and displayed. Also, imaging plates with smaller pixels will record more detail. This increased detail may not be appreciated unless the image is magnified. Also, radiographers must realize that radiologist monitors will display more detail than do the monitors available to the radiographers. Small objects are easier to see in high contrast images. Controlling fog and quantum model can play a major role in achieving this end. Use of collimation and grids can control fog, while careful selection of proper MAS can minimize quantum model. Thank you for your attention. This has been Spatial Contrast and Resolution presentation.